Hi everyone. Today I'm going to be discussing the solution to the recent cook-off problem, perfect squares. Uh, but before I get into the solution, I'd like to quickly remind you about uh, the subscription program that CodeChef has partnered with an academy to review. Uh, so the subscription program has a list of curated courses to help you get better at computer programming. There are lots of courses which are taken by top educators, like and the educators are ICPC World finalists and software engineers at popular companies like Google, Flipkart, LinkedIn, etc. So for uh, a reasonable amount, like per month, you can get access to these courses where you can interact with the educators live on the chat box, and you also have dedicated contests and questions. And yeah, feel free to check it out at unacademy.com/go/computer programming. Uh, that's it about the subscription program. So getting back to the problem, I hope you've read it. So the question is, we have to find the number of uh, integer sequences of length n, such that the graph of uh, uh, the special graph where you connect two nodes, if their product is a perfect square, uh, is a subgraph of g of a. So essentially, uh, if you look up the details, the problem is actually uh, uh, okay. So let's see what g of a is for the given graph, which is so you have n intervals, L1, L1, L2, L2, and so on, Ln Rm, and the graph that you're given is this one. L1 and L1 plus 1 are connected, L1 plus 1 and L1 plus 2 are connected, and so on to R1 is connected, and similarly for L2. Sorry. This is the graph that you're given. Let's say this graph is G. Um, and there's also another graph, G of A, where uh, AI and AJ are connected if uh, are connected. That is, I and J are connected if AI into AJ is a perfect square. Okay, we want G to be a subgraph of G of A. So, to say what it says is G of A should contain all these edges, L1 to L1 plus 1, L1 plus 1 to L1 plus 2, and so on. And it's also given that these intervals are non-overlapping. Non-overlapping. So, right. So all these edges must be present in G of A. So that's the meaning of G should be a subgraph of G of A. So if all these edges are present in G of A, that means that AL into al1 into al plus 1 is a perfect square. And similarly, al1 plus 1 into al1 plus 2 is also a perfect square, and so on to ar1 minus 1 to ar1. And all these numbers should be perfect square for every interval. Okay. So uh, we have to find the number of uh, integer sequences a1, a2, so on to an that satisfy this property for m different intervals L1 R1, L2 R2, so on to Lm R1, and uh, the numbers must be from 1 to k. So uh, the problem statement can be reduced to finding the number of integer sequences such that for the given intervals, every adjacent elements product is a perfect square. Okay, and we need to count how many such sequences there are. So since the intervals are non-overlapping, right, we can assign numbers to this interval independently from the other intervals. So we can find the number of uh, arrays of length r1 minus l1 plus 1 that satisfy the given property, and then just multiply the answer for uh, all their m intervals, and the other numbers, uh, say al minus 1 to a1, etc., and then arm plus 1 to an. These numbers can be anything because there are no constraints on them. So uh, we don't have any edges for these numbers. So there are no constraints for these uh, elements. So each of them can have all k values. Uh, so each of these numbers can have all k values, and then we can treat these intervals as separate. Okay, we can find answers for each of them and multiply. So essentially what we have is, let's find the number of integer sequences with all elements in the range 1 to k. Okay, and satisfying this property that a1, a2, a2, a3, so on with size s, let's say. Yes. All these numbers should be perfect squares. Let's say the number of subsequences of a size s, and all the elements belonging to the range 1 to k, and the product of every two adjacent numbers being perfect squares, must be perfect squares. Okay, well, let's count the number of such integer sequences, and let's say that that number is f of s. Okay. If we are able to find f of s, then the answer to the problem is only r1 minus l1 plus 1 into f of r2 minus l2 plus 1, so on, r minus l plus 1 into k power n minus the other numbers, r1 minus l1 plus 1, r2 minus l1 plus 1, so on. Okay, so if we are able to find f of s for these numbers. Let's call this S1, S2, S1, if we can find that, then that's it. So essentially, the problem is finding out f of s for m different values. So the tough task is to find this out. So in order to make the adjacent elements' product to be perfect squares, uh, how can we do that? So uh, if a number is a perfect square, then every prime number occurs even number of times in the prime factorization. So for example, if you have, yeah, so if you have x squared, right? So uh, every prime factor, the exponent will be even, right? So we want a1, a2, a2, a3, and so on till as minus 1 to as. All of these numbers should be perfect squares. So every prime number must occur even number of times in this product, in this product, and in this product. Okay. So let's move on. So suppose a prime p occurs odd number of times in AI. If it occurs odd number of times in AI, then uh, it should occur odd number of times. Then it should occur uh, odd number of times in AI plus 1 as well, right? Because only then AI into AI plus 1 will be a perfect square. Because if a prime occurs odd number of times in only one of these two, then in the product also P will occur odd number of times in the prime factorization, and it won't be a perfect square, right? So, uh, okay. So if it occurs odd number of times in, let's say, A1, okay, if P occurs odd number of times in A1, then it will occur odd number of times in A2 as well. It will occur odd number of times in A3 as well, and so on. Okay. So if a prime occurs odd number of times in any one of these elements, A1 through AS, then it will occur odd number of times in all the other elements as well. So, uh, so it will look like something like P times some number, P times some number. So all numbers will be uh, will contain this prime P. If at all it occurs odd number of times in any one of the sequences, right? So we know that the set of all valid integer arrays will look something like this. P1, P2, some prime, some primes P, then followed by a perfect square. So uh, let's consider the first element, and let's say that all the primes that occur odd number of times in that element are P1, P2, and so on to Pk. Okay, so these are the only primes that occur odd number of times in A1, let's say. Okay, then all these primes will occur odd number of times in the other elements as well. And what you have left in the prime factorization after removing these primes will be a perfect square. Okay. Similarly, if we extend it to these numbers, you get b2 square and so on. You want to do okay, and then B as well. So apart from this common factor that contains primes only once, apart from this factor, which is present in all the elements of the array, all other factors are perfect squares in the array. So any sequence that we're looking for that has this property that all adjacent elements is product should be perfect squares will be of this form. So this is the first observation that's easy to make, I think. So once you get this, so how many possible integer sequences are there? So let's fix this term uh, p1, p2, pk that occurs in all the elements in the sequence to be x, let's say. Then b1 can be any square that's less than k by x, right? Because uh, if this factor that occurs in all the numbers is already x, we want the product to be less than k because all elements should be less than k in the answer. So the number of choices that you have left for b1 is all squares that are less than k by x. So uh, this says that there are square root of k by x possibilities for b1. That is 1 square, 2 square, so on to square root of k by x square. Okay, so there are only square root of k by x possibilities for the leftover factors of a1. If you say that it's divisible by x, so then the total number of sequences is square root of k by x over s. Okay, uh, so iterate through x and we can find the total count. So the total number of sequences will be sum over all x such that x uh, does not contain any prime twice in the prime factorization. Uh, Square root of k by x power s. Okay, and essentially what this means is x should not contain something like p1 square. So we can call x to be square free. Uh, so x is a number that does not contain any square as a factor. So it's only a product of primes, like so. Okay. Such if such a number is a factor of any sequence in any any element of the integer sequence, then it will be present in all the elements. Only then you can have, for example, here any two adjacent elements. If you take, it ends up being a perfect square, right? Because if p1 is in the first term, p1 should be in the second term as well. So their product is ends up being a perfect square. And to count the total number of sequences, all we have to do is sum over all x such that x does not contain any square factor, and uh, square root of k by x power s. Uh, Unfortunately, in the problem, k is 10 power 14, so we cannot hope to evaluate this for all numbers x from 1 to k. Okay? But there's an interesting fact that uh, although there are k is very large, okay, so uh, 10 power 14, the this term here, okay, it's always less than or equal to square root of k, right? Uh, so there are only square root of k different possibilities for this term. Okay. So as an example, let's take uh, k equal to 23. Okay. So for k equal to 23, x can be 1, 2, 3. X cannot be 4 because uh, it's a square number. Then we have 5, 6. 6 is 2 into 3, which is perfectly fine. 8 is x cannot be 8 because it contains 2 square. Right? We only want numbers that are square free. Okay. Uh, 10. Similarly, 9 is not possible. We have 10, 11, 13, 14, 15, 17, 19, 21, 22, and 23. Okay. Uh, what about square root of k by x? Square root of k by x will be uh, the integer part of square root of k by x, which is what we're interested in, will be 4, 3, 2 for these guys, and from 7 onwards, it will be 1. Okay? So a lot of these numbers, they are equal. Okay? And what we will try to do is we will try to sum up those values that are repeated and almost equal, and we will try to sum them all up at once so that we will spend only square root of k time in evaluating this expression, okay, which is our final goal. Okay, so this is f of s, right? Uh, Finally, uh, let's go over. Huh? Okay. So we know that square root of k by x has only uh, less than square root of k different values. Okay. Uh, Different values. But now, how to obtain them, right? Uh, how do we obtain these different values? So as you saw here from this example, there is a range of there's a continuous range where all the numbers are equal. Okay, and there are square root of k max, square root of k such ranges of uh, equal elements, and we would like to find all these ranges. Okay, and evaluate the sum for each range uh, quickly. So instead of iterating through these and 2 plus 2 is 2, we will compute them all at once because we know that they are all same. Okay? So that will optimize the evaluation of this function. Uh, Going over, so uh, how to obtain the different values? Well, we can easily see that if square root of k by x is r. Let's say the value is r. Okay, then uh, square root of k by x must be uh, within r and r plus 1. Okay, uh, this means uh, k by x is r squared and r plus 1 double square. This means x is less than or equal to k by r squared, and x is greater than k by r plus 1 double square. So for all x belonging to this interval, uh, you see, k by r plus 1 double square to k by r square. So for all x in this interval, square root of k by x will be same and will be equal to r. So we can obtain these ranges. We can obtain these ranges for which square root of k by x, the integer part of square root of k by x, takes the same values in uh, by using this formula. Okay, so if square root of the integer part of square root of k plus 1 is, for example, if it is 2, then uh, x must belong to 23 by 9 to 23 by 4, which is 23 by 9 is, let's say, starting from 3 and ending at 5. Okay. So for all numbers 3, 5, for numbers 3 and 5, uh, square root of k by x is 2, and for starting from 6 onwards, it's 1. Okay. So, like so, we can iterate through the square root of x different ranges. Okay, and find out how many numbers are square free. So here we obtained an interval 3 to 5. So I know that from 3 to 5, square root of k by x is 2. Okay, and I still have to iterate through the square free numbers. So from 3 to 5, the number of square free numbers is 2. So I know that uh, the summation expression will consist of 2 into 2 power s. Right? And for each of those uh, square root of k different ranges, for each range, remember that there are only square root of k of them. Uh, Find this term is constant in the range of s, and here you have the number of uh, this is equivalent to r. Here we have the number of square free numbers from k by r plus 1 squared to k by r squared. Okay. So essentially we're compressing the summation that had k different terms to a summation that has square root of k terms. Okay. So that we can evaluate quickly the sum. let's call uh, this number r, sigma r power s, and let's call this number of square free numbers in this range to be g, g of uh, let's say summation can be replaced by sigma g of k by r squared to k by r squared. So how many square free numbers are there from k by r plus 1 the whole square to k by r squared times r power s, and r varies from 1 to square root of k. Okay. And remember that r cannot be every such value. Like for example, for k equals 23, we had 4, 3, 2, 1. So in general, it could be possible that uh, this interval doesn't exist at all. Okay, so for k equal to 10 power 40, it turns out that there are only 10 power 5 such terms. We know obviously it cannot be more than 10 power, square root of k, which is 10 power 7. But if you actually compute the number of some of these ranges are zero or length less than 1, and they don't contain an integer in them. So uh, essentially it amounts to only 10 power 5 such terms. And for each range, we want to find uh, the number of square free terms. Okay. Terms in the range. In range uh, L in range k by r plus 1 square to k by r square. Another way to think about this is monthly the number of square free terms, uh, which when multiplied with r square is less than k. Okay? And we can calculate this number with these sums by inclusion exclusion. So let's start with all the k. Let's compute the answer. Let's say for r equal to 1. Let's consider r equal to 1. We need to find the number of square root numbers in the range uh, k, the range k by 4 to k. Okay. And in order to calculate this, we will say this is k minus number of numbers less than k and divisible by 4. And then again subtract the number of numbers less than k divisible by 9 and so on. So if we uh, using the inclusion exclusion principle, we can find the number of square free terms in this range for each r like so. Okay. Uh, that's one way to calculate it. Uh, but a more efficient way is let's say uh, of r is the number of square free numbers such that they are less than or equal to k by r square. Okay. So if we define count of r like so, then essentially what we want here is the sum in this range is count of r minus count of r minus 1, right? Because, sorry, count of r minus count of r plus 1. So number of square free terms in this range is the same as number of square free terms less than k by r square minus the number of square free terms less than k by r plus 1 square. Okay. Uh, okay, so let's define count of r like so. Uh, count of k is obviously 1 because uh, so count of anything greater than or equal to square root of k is 1 because k by r square will be less than 1. Right? So square free numbers, so we can obtain count of r for large numbers easily. So count of k is 1. For the smaller numbers, what we can do, let's say count of I, if we want to calculate, let me just do the same variable. Count of r, okay, is the number of square free numbers less than k by r square. Okay. Initially, let's say let's uh, count all of them. Okay, and let's subtract those numbers which are divisible by some square. And let's say that the smallest prime factor present in the square is j. Okay, if the smallest prime factor present in the square is j, then uh, the number will be something like j squared into some other number, right? And if we uh, remove j from, uh, if we look at these numbers, this happens to be a square free term. Okay? So what we can do is subtract count of, let's say, j into r. Uh, for all j from 1 to square root of k, or for all numbers such that j into r is less than or equal to square root of k. Okay, and this formula gives the right answer. Okay, so let me explain again why this is true. If what we're doing here is counting all numbers and subtracting the number of numbers that are divisible by some square. Okay. If a number is divisible by some square, let's say that the largest square divisor is j. Then uh, if the largest square divisor is j, then the number will be j squared into something that's square free. And uh, j squared is something that's square free. So this can be written as j into something that's square free. Because if there were some squares here, then that square into j square would be a larger square divisor. So if the largest square divisor of any number that's less than kbr square is j, then that number will be j into something that's square free already. Okay, so essentially what we want is we already know the count of square free numbers for large numbers correctly. So uh, we calculated the answer for count of k to be 1, or even count the square root of k to be 1. And we need to calculate count for the smaller r's, right? And so when we're calculating count of r, we know that count of all the numbers greater than r have been previously calculated. So we're going to do something like uh, uh, a recurrence from backwards, from square root of k down to 1. And we say that count of r is k by r squared. These are the total number of numbers minus count of 2y, 2r. So this will have all the square numbers that have the maximum square as 2. So 2 square is the maximum square that divides uh, these numbers, and we can subtract them from k by r square. Similarly, subtract from 3r and so on. So we'll count xr until we exceed square root of k. Okay, and uh, the complexity of this reference is similar to that of C, right? And we can get count of r in uh, square root of k log k, where square root of k is approximately 7, and this is very uh, efficient, and we can do this pre-calculation beforehand. Okay, and now finally we have our answer is sigma out of r into r power s, as r varies from 1 to square root of k. Okay, and uh, we need to evaluate. So this is f of s. We saw how to find count of r efficiently. We can pre-calculate this for all possible r's, uh, and for all numbers from 1 to square root of k. And then uh, still we have to find f of s1, f of s2, so on to f of sn. Multiply all of them and get our answer. But still, we cannot afford to do because m is 10 power 5 here, and k is 10 power 14. We cannot afford to do. We cannot afford to even calculate the sum for each s, right? Because m is 10 power 5, and square root of k into m is not fast enough to get AC. So let's see how to find this summation uh, for m different values of s efficiently. So at this point, we will need some math from generating functions. So let's define, let's consider this polynomial 1 by 1 minus, or rather, let's consider r by 1 minus rx. This is 1 of r plus 1 of r into rx plus 1 of r into r square x squared plus etc. Okay, so if we consider this uh, polynomial, this is a technique to evaluate uh, this summation for all the s different values simultaneously. I mean, quickly. So what we have on the right hand side is the sum of all the terms, s equal to 0, s equal to 0, s equal to 1, s equal to 2, and so on, multiplied by this variable x and creating this generating function. Okay, for a single r, or for by fixing r and varying s. And if uh, let's consider the summation on the right hand side. We have sigma of r by 1 minus rx. Left hand side is sigma count r count of r rx, and so on. Okay. So the right hand side is essentially f of 0 plus f of 1 x plus f of 2x squared plus so on. And the left hand side is this polynomial. It's a sum of say r equal to 1, okay, and there, although I'm writing square root of k here, some of the terms have count 0. So if we consider only those terms with positive count, that happens to be around 10 power 5. So there are 10 power 5 terms on the left hand side, and on the right hand side you have on the right hand side is the generating function expansion. Okay, and we would let's try to simplify this expression. Here we have uh, sum of m, or let's say, let's call this r, sum of r partial fractions, and we can evaluate this quickly by using divide and conquer. So what we want is we have, let's say, count 1 by 1 minus 1 x plus count 2 by 1 minus 2x plus so on. So count m by 1 minus 1 x. We want to simplify or simplify the sum of these partial fractions. So we can divide it into two, and evaluate this half separately. Okay. What I'm trying to do here is I'm trying to expand the partial, this simplify this summation into a polynomial by polynomial, okay? So that I can find the coefficient of x bar s. So the coefficient of x bar s is what we want, which is f of s. So by writing these fractions down on the left hand side, if I can simplify this partial fraction into numerator by denominator, then I can find coefficient of x bar s in this expression uh, quickly. And all right, so uh, what will be the degree of the two polynomials, the numerator and the denominator, if we take LCM? The LCM is 1 minus r1x into 1 minus r2x and so on till 1 minus rrx. The LCM's degree is r, right? And so similarly, the numerator terms are also degree less than r. So I can simplify this to a polynomial of degree r in the numerator and polynomial of degree r in the denominator. Okay, and the task is to find coefficient of x bar s in this polynomial. But first, we need to evaluate or simplify this summation, right? We cannot afford to take LCM for each term and add them individually because r is 10 power 5. So here what we can do is we can do a divide and conquer, split them into two halves, evaluate each half separately, and get the term. So let's say that the left half was PL of S by the, or let's say numerator and denominator. Let's call it NL of X by DL of X. And then similarly the right hand side, the NR of X by DR of X. Now we can simplify this as NLDR plus NRDL by DLDR. And okay. So this is a, remember that uh, we divided into two. And let's say, suppose recursively we can find uh, the r by 2, first r by 2 terms and the second r by 2 terms, simplify to polynomials nl by dl and then r by dr. Then I can combine these two like so. So the degree of this guy is like r by 2. So all terms here have degree r by 2. And the degree of this term here in the numerator, it's a degree r term. And the denominator is also a degree r term because we're multiplying two polynomials of degree r by 2 each. Okay. And we can get polynomials n by d like so. Okay, and let's say t of n, t of r is the time complexity for a polynomial with degree r. You can write that as 2 times t of r by 2 plus cost of multiplying. So uh, once we have NLDL and RDR, we can evaluate NR into DR. This is a polynomial multiplication of two polynomials with degree r. That can be done using FFT in R log R. So all these multiplications can be done in R log R, and uh, we can get. We're going to store this fraction in the computer as a numerator polynomial and the denominator polynomial. Okay, and once we have that, we can say that the time complexity is R log R. TFR is 2 times TFR by 2 plus R, and uh, this reduces to R log R square. This implies T of R is R log square R. Okay, and there's a nice blog in CP algorithms under polynomials for uh, evaluating such expressions. I would ask you to check that also, because I cannot cover this in depth in it's not practical to cover this topic in depth here. But uh, similarly, once we have the numerator and the denominator, we can find the coefficient of x bar s in let's say n by n. This is the final step that we have to find. Find the coefficient of x bar s for each s from 1 to the square root of k terms, and that can easily be done uh, by taking polynomial inverse of t. Okay, we find out all these terms modulo x bar s. Okay, so we can find d inverse modulo x bar s and multiply the polynomials like so to find all the solutions. And once we have, so we will get a polynomial uh, like so, f of 0 plus f of x plus square so on to f of s x bar s. And here we know that the length of all the intervals are less than 10 so s is 10 so all we have to do is we have to calculate d inverse modulo x bar 10 which can be done in 10 log 10 squared, and then we multiply the two polynomials to get all values f0, f1, f2, and so on to fs in 10 log 10 squared 9. And once we have all the values individually, we can just multiply them to get the final answer. So that's the summary of the solution for this problem. So, well, firstly, figuring out to some. Let me just summarize the solution a bit. Uh, Firstly, you had to observe that uh, we can find the answer for each interval uh, separately, and we can multiply the possibilities, and then figuring out that uh, every adjacent pair will be a perfect square only if all the prime factors occur odd number of times is common to all the elements. And once you figure that out, you will find yourself with this expression, uh, sum of square root of k by x, where x varies from 1 to k. And then you have to see that a lot of terms in this expansion will repeat. And so to optimize that summation, we will find compress the range 1 to k to these square root of k intervals, with each interval containing uh, having the same square number of possibilities for the squares. And then once you find that, uh, calculating the number of square free terms can be done by inclusion exclusion. That's a nice recursion that you can get. Uh, this formula, this formula, calculating the number of square feet terms in that range. uh, in reverse. We can do this recalculation quickly, and uh, again, this is square root of k. All these work is done in square root of k, and once you have that, you will find yourself with this expression that you have to calculate for different powers, and you can use generating functions to simplify uh, to rewrite the summation as a polynomial, and then you can see use divide and conquer and end of t to find out the polynomial efficiently in 10 bar 5 log 10 bar 5 square time. So yeah, a lot of difficult concepts were involved, but uh, check the editorial out also, and hope you got like a nice I hope you got a brief idea of this solution. And uh, that's it from my side, my end. Thanks for watching.